Lab 3, Mass of a Black Hole. The objective of this lab was to determine the mass of a black hole using given position data of a nearby star. In order to determine the mass, we used the computational model based on Newton's second. I determined my mass of the black hole to be 7.999 e to the positive 38 kilograms. So in order to determine the mass, we must take into account principles of physics and some formulas here that would allow us to apply into our computational model, which we will use to apply in our computational model. So in order to determine the change in position we use change in position over change in t, which would give us b, and change in the velocity, which would be final velocity minus initial velocity, which we did for over the period of each position in the data set. In order to get the momentum, the change in momentum, we would use the change in velocity times the mass of the star. And in order to get the net force, we would represent that as change in momentum over change in time. The net force could be broken down into the parallel component, which is magnitude, and in addition to the perpendicular force, which is the change in direction, which gives it the curvature. And dBdt can also be broken down into the parallel perpendicular components. So we would use some of these formulas to give us the trajectory of the star. In order to calculate the mass of the black hole, we would use the gravitational force formula given to us, which is g times m of the star times the mass of the black hole over r squared radius, which in this case would be the distance between the star and the black hole. G is equal to 6.67 e to the negative 11. So here we have the Python code that I used to create the computational model. Not sure what that was. Anyway, so I created a black hole attribute so we can actually visualize the black hole in the model. And as you can see, the mass of the star is 2.7615 E227. The position of the black hole is given by the vector over there. So I represented the black hole using a total, which I set to 0, and then the time change, and I set the initial time change to 0. The delta t would be 86,400, represents 1 day. So we have the main punchline of the lab. In order to calculate V initial and V final, we represent that by that coding. P initial, P final would also be represented by, as we said, star M times V initial in this case, and then star M times V final for the final momentum. So let me go down. So here we have the attribute to represent the mass of the black hole, which would equal the magnitude of F net times the magnitude of star position minus black hole position squared over G constant times star mass. And let's run the model. So as you can see, I have a little bit of trouble getting my arrows so pointing the correct direction. I'm assuming that one component of the net force was overwhelming the other force, which is the reason why I only see one of the arrows, which represents my parallel component. could also be due to the aeroscale I used. Although I did try several different aeroscales, I never did quite get the three components to display at the same time.